I'm usually, the Elixir conferences, I'm usually talking a lot about Elixir, as expected, and as the language as a whole. And but we've kind of like being very explicitly telling that development in Elixir, the language itself, it has been kind of slowing down over the last year a little bit more. And it's good because it frees up time, like the members of the Elixir team to try out different ideas, explore different ideas. And today I want to talk about a new project, Broadway, which has been developed at Plataformatec. Marlos was the person, he's not here, but he's the person that led the effort. And so I want to talk about this project, and it's really interesting. Even though it's not Elixir itself, it's really interesting because the path that led us to this project started with Elixir, as we're going to see in this talk. So it's really the road, everything we kind of went through and tried out. And what made this talk really interesting is because who has here been to at least one previous Elixir conference Europe? 2? All right, 3. All right, yeah, so depending when you have been at the Elixir conference, you're going to see, oh, I have seen those slides before, because it's really have been a journey for us to be where we are today, and maybe Broadway is kind of the last step in this journey, maybe it isn't, right? So let's get started, right? So I'm talking a lot about Broadway. So what is actually Broadway? So before we go and tell this whole history and talk about this journey, let's do a very quick sneak peek on what Broadway is about. So Broadway is a new library for concurrent and multi-stage data ingestion and data processing with Elixir. So imagine you have this problem. You want to fetch data from Amazon SQS or Google Cloud PubSub, or RabbitMQ, Apache Kafka, doesn't matter. And then you want to, of course, process this data concurrently. You want to process this data that is coming to the system as fast as you can. And then, for example, if you are working against Amazon SQS, one of the things that you want to do after you process this data is that you want to batch this data, because for example, if you want to be efficient, both in terms of time and of money, you want to do batches of the data when you go acknowledge it on Amazon SQS and other places as well. And then after you batch the data, you may want to publish it to another source, right? Maybe what you're doing is just receiving data from external system, processing it in some way, and then write it down elsewhere. So that's the problem. And Broadway allows us to do all of those things with pretty much this. So what you do is that you're going to define a module called My App Broadway, and we're going to say, I want to use Broadway, which is our default things. Every time we are building on top of something, it's very common for us to do use Broadway. And then you're going to define 3 functions. Start link, and this start link is basically where you define your Broadway topology. And then you have 2 other callbacks, handle message and handle batch. And this is where you're going to put your business logic. So what do you want to do on each message? You just write that down in handle message. Oh, and every time you have a batch, what do you want to do with it? Then you just implement that in handle batch. So that's it. Everything else, they're going to take care of it for you. You don't have to do anything else. Okay, so, and how does start link looks like? It looks like this. So you're going to say, look, I want to start this Broadway process, or rather this broader supervision tree. And you say, look, it has a name, and I have some producers. My producers, they're coming from SQS. Here's the queue name, and I want to have 4 producers, 4 things getting data from SQS at the same time. And then I want to have processors. Those are going to process each message, and we'll say we want to have 20 of them, 20 running concurrently. And then you can also say, I'm going to have some batchers, and the batchers, I'm going to have 2 of them. You can see we have stages 2, and you can say, and I want to batch according to 2 parameters, the batch size or the batch timeout. So the goal is to get 10 messages in a batch within 1.5 seconds. If I can do that, then if I can get to 10 before the timeout, then I send that batch. Otherwise, as soon as I reach the timeout, I send the batch with how many messages I have in that batch. And that's it. That's all you have to do, right? And we'll take care of everything else. So, right? And then you're ready to write your business code, your business logic, and focus on the things that matter to you, to your company, to your domain. So this is Broadway today, but in order for us to get this and have Broadway as an abstraction, as I said, it was a quite of a long journey, and that's actually what we're going to talk about today. We're going to talk more about the journey than about Broadway itself. So we're going to talk about three things: collections, GenStage, and Broadway. All right, so who here is already using Elixir, is programming Elixir, has used Elixir collections, right? You wrote a list. And is somebody using GenStage in production? Oh, that's amazing. And somebody has already tried Broadway? All right, a couple hands, that's great. All right, so those are the three things we're going to talk about. So let's get started. Collections. Okay, so when I started working in Elixir back in 2011, it started as a failed prototype. I started Elixir as a fun project. Mostly, I don't have a computer science background, so I did not know exactly how programming languages work or are designed or are structured. So it started mostly as a fun exercise. And what I did is that because I was already starting to use the Erlang virtual machine and enjoy it very much, I said, okay, I'm going to try to write a programming language for fun on top of the Erlang virtual machine, and kind of like trying to do two things at once, right? Like learn more about Erlang and the virtual machine and learn more about how programming languages work. And so I did this prototype. It failed in a bunch of different ways. But eventually, after some time, I had like this thought in the back of my head, like saying, you know what, there is an opportunity in here for something, okay? And I spent quite some time thinking, like, if I were to write an actual programming language, not just a prototype thing, in the Erlang virtual machine, what are the features that I want to have in that language? And there were two main things. One is metaprogramming, so we hear a lot about metaprogramming. And the other one was data polymorphism. And there is one kind of data, one particular, I wanted to focus a lot on data polymorphism or in data types in general. I want to have very good data types, very rich library for us to work with those data types. And there is one particular data type, right, that we use a lot, which are collections like lists, sets, maps, dictionaries, queues, right? So I wanted since the beginning, I ended up focusing a lot in collections. I want to have very good abstractions for working with collections. So with time, I did not have those requirements up front, but we've built those requirements with time. But we ended up building this list, which today I would say, you know, I want collections to be polymorphic. And what does this mean? Polymorphic is multiple forms. So if you're going to have a bunch of collections, as I said, lists, sets, maps, and so on, I do not want to have like one module to work with each collection, right? And then implement a bunch of stuff, sometimes have conflicting names. I wanted to have one single module that could work with a huge variety of collections. And today in Elixir, that's the none module, as we'll see. And then the other requirement that we built with we built with time is that we also want those collections to be extensible. So if you're going to have a module in Elixir that works with a huge variety of collections, we do not want this module to work only with the collections that ship as part of Elixir. We don't want it to work only with the collections in the standard library. We want it to work with any collection that you as a developer may write at any moment. So we want it to be extensible, open. We also want it to be general. We want it to work not only whatever we're going to do, whatever abstraction we're going to come up with. We do not want it to work only with like data structures that are in memory, again, list sets, but you also want to work with resources. So yeah, like if I want to work with a stream of data coming from the database, that should work as well. Or if I want to work with a file and use the same APIs to traverse a file, we want that as well. And for lack of a better word, we also want it to be tunable, right? So it means that we want to go from eager to lazy to concurrent to distributed. And we are able to achieve a good part of those requirements with an abstraction that later I went on and wrote and documented it called Red Disease. So I'm not going to go into detail about what Redis is about, but we do have an article in the Plataformatec blogs. If you search introducing Redis, Plataformatec, you're going to get there. So you can read more about the internals. But what it means to us as developers is that we can do things like this, right? So collections, they are polymorphic. So map, I can pass it a list, or I can pass it a range, and it knows how to traverse both, right? They are also extensible because behind the scenes, the enum module uses a protocol called enumerable. So if you want the functions in the enum module to work with your own data types, your own collections, all you have to do is implement the protocol with those 4 callbacks, and that's it. And they are also general. I can pass it a list, so I can map a list of strings, and those strings, they are in memory, of course. Or I can pass it a file. I say, look, I wanted to traverse this file and convert all the lines in this file to uppercase all the lines in this file as we do it. And this is really nice because it takes care of everything you have to do, all the manual resource management. You don't have to open the file, don't have to close the file. You don't have to configure the way you want to traverse the file. It's already going to take care of all those things in the most efficient way as possible. Okay, and we were also able to make it slightly tunable, right? So we can see here we have like 4 kind of ways to tune it, and we're able to take the first step, which is to make it from eager to lazy. Let's see what that means. So in Elixir, Elixir is it's a strict language, which means that when you call a function and you execute that code, that function is going to be executed where you wrote it, right? So for example, if you have a list 1, 2, 3, and then you map over that list twice, printing the elements of the list, right? What is going to happen? You're going to have 1, 2, 3, and then you say in the map, we are going to go over the whole list, print all the elements, and return a new list at the end. Right, and then you call a nummap again, which means we go through the whole list again, printing each element, right? And then we finally return the list itself. So as soon as we call a nummap, right, it's going to go and traverse the list. At that moment, it's eager. But in Elixir, you can make everything lazy by simply replace the enum module by the stream module. Okay, and you can see that as soon as we do this, it no longer executes anything. It just returns a stream, and a stream is a recipe. It doesn't execute the code. It just knows, look, when I want to traverse this collection, I will have to map and print and map and print, but it doesn't do the work just yet, right? It waits. And then if you want the stream to actually, so it's lazy, right? It's just waiting until you actually need the results. And if you want the stream to actually compute something, then you need to say something like stream run, or you need to call a eager operation on it, like enum to list. And when you do this, you can see that it does execute, it does print each number twice, but now they're in different order. Before it was 1, 2, 3, 1, 2, 3, and now it's 1, 1, 2, 2, 3, 3. Because the stream, it fuses all the operations. So it has to traverse the data type just once. And why does this matter? This matters because, for example, if you have really large lists and you are using enum, right? Every time you call the enum function, you are traversing the whole list and creating a whole new list. With stream, you don't have to do that. We fuse all the computations, and we have to traverse the collection only once. So it allows us to work with really large collections. Like if you are traversing if you have a 1 gigabyte CSV file. If you use enum, you're going to load that whole file into memory, right? And then you're going to go line by line, create a bunch of intermediate lists. It's going to take a lot of memory. But with stream, we never load the whole file into memory. We only work line by line, okay? So it allows us to work with really large collections, potentially even infinite collections, okay? And this is what we were able to achieve by the time we released Elixir 1.0. We were quite happy with what we were able to do, with what we were able to get out of the radices as an abstraction. So, we're able to make things polymorphic, extensible, they are general, and we're able to make the first step, okay, in going from eager to lazy. So, after Elixir 1.0 was out, we're like, okay, we are now ready to try the next step, which is to make things go from lazy to concurrent. And that's the part that's interesting, because exactly if you go see the previous keynotes that we've given in different ElixirConf events, you see the journey that I'm going to talk about. I'm going to give a summary, of course. You see it happening live, like as we are trying things and running into mistakes or running into limitations, right? But here's what we are trying to do. We want to make it go from lazy to concurrent. So our first idea was something called pipeline parallelism. So imagine that I just talked about this large CSV file example, right? So imagine we have this thing. So we want to open up a file stream, something that knows how to traverse a file. And so imagine that's a CSV file. Then we're going to get line by line. We want to split the line on the comma, for example, and then we want to traverse, we want to transform those things. So we have like 4 steps there in the middle. And then at the end, we say stream run. I want to execute this stream finally. So our first idea on how to get concurrency would be, well, what if we added stream async calls between those steps? And every time you do a stream async, what we would do is that we would get the previous step and make it run on a separate process. And then that process is going to process this data and send it to us, right? So if I called stream async here 3 times, at the end would have a topology that would look like this, right? So very straightforward, like we're just sending things forward. So we start with a file, and that's doing things in one process, and then we send it to another process, which is going to do maybe split the lines by comma, async, and then we're sending it for all of those processes until we get to the end, right? Unfortunately, this approach has many issues with it, as we found out. So the first thing is that who has to add the stream.async calls? It's us, right? The developers. So it's error prone, right? Because everything is manual, right? And it's really hard. It would be really hard to optimize, right? Because maybe you benchmark in your machine and you add the stream async in the places that are optimal for our machine, but when you're going to run in production, it's a different machine, and maybe those are not the best places. So that's one of the issues. The other issue is we are moving the data a lot between processes, right? Like every time we call stream async, it's a new process, so we are going to process the data and then send the data to the other process. And what does it happen when we are sending the data between processes? The data is copied, right? Because the processes, they are isolated, they cannot share data. So it means that if you actually add stream async too much or on operations that are too small, it could actually make everything less efficient because we'll spend a lot of time just copying the data. So we don't want that, right? So we are moving the data a lot, while ideally what we want to do is that we want to move the computations, because the computations, they're cheap, they're just code, right? So we usually want to leave the data in one place and have to shuffle it around only if we actually have to. And the other thing is, since we are starting to talk about processes, and here's particularly where I think the Erlang virtual machine made me a better developer, because if it was like José 10 years ago, I would probably have built this and be really happy that it works and not worry a lot about a bunch of other stuff. But because we are talking now about processes and exchanging data between processes, we also have to ask those questions. How to reason about fault tolerance, right? Wait, if I have a bunch of processes and one of those processes fail, how I'm going to react to it? Like, how I'm going to handle this? So we started to think, okay, we have to have a good model to reason about fault tolerance. And this model, where everything is just a simple pipeline, do not seem a very good model for that, because everything is just going to crash. And the other question is how to provide back pressure, because we are sending messages between processes, right? And messages, they go to an inbox, right? To a message queue. What happens if you have one step in your pipeline that is super slow? It's just going to get messages in its inbox, and that message queue is eventually going to grow too big, or going to run out of memory or something like that. So we started to ask those questions. We saw those limitations, started to ask those questions. And then eventually we realized that we were attacking the problem from the wrong angle. We were starting from the collections from the data types perspective, but really what we should be looking at is to create a new abstraction. Okay, so usually when we are thinking about processes and abstractions around processes, we are talking about gen something, right? We have gen server, we have gen event, gen state machine. So we were like, we need something new, right? And we actually built 3 or 4 prototypes. We tried like gen router, gen broker, and they all had like some flaws, some limitations. And eventually we settled on GenStage. Okay, so this is the first part of the talk, all right? So this is about how at the beginning we wanted to have this very strong focus on data types, data polymorphism collections, and with time we've built like this plan, this list of requirements, and we're able to, and we were slowly, as we try different things, build prototypes, we were progressing on this line, okay? And that eventually led us to GenStage. So what is GenStage? It's a new behavior, okay? It's a new behavior for us to describe how we want our processes to work. And the idea is that we can exchange data between stages transparently and with back pressure, right? So we can see some similarities to what we were talking about, right? So we are still transferring data, but now it has incorporated back pressure, which we've noticed it was an important thing that we had to add to our model. And we have 3 kinds of stages. We have producers, consumers, and producer-consumers. So it would look like this. So I have a producer, and then you have producer-consumer, 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 and you end with a consumer in the middle. It's similar to what we were doing, but as we said, we added back pressure. So let's see how it looks like. So the way back pressure looks like in GenStage is that everything is demand-driven. When you establish a connection between a producer and a consumer, the producer cannot just immediately go and send data like, hey, take this, right? It cannot do that. What the first thing that needs to do is that first the consumer subscribes to the producer, okay? And then after the consumer subscribes, it sends demand. It say, hey, producer, I need like 10 events. I can process 10 right now, so send 10 events to me. And then the producer is going to eventually send those 10 events. It may send 10 at once. If it already has those 10, it may send 2, and then 3, and then 5, whatever it wants. And that's it. So everything is demand-driven. The consumer needs to ask for stuff. And the nice thing about this approach is that we can push the back pressure to the boundary of the system. Because if I have 3 processes, here's what's going to happen. C is going to ask B for 10, and then B is going to ask A for 10, right? And then A is going to send 10 to B, and B is going to send 10 to C, right? So if you have a very big pipeline, the demand goes all the way up to A, which is your producer. A is likely the one that is interfacing with the external system. It's going to be interfacing maybe with a file, maybe with RabbitMQ, maybe with Amazon SQS, right? So it's at the very front of your system, and then you know exactly how much data you should get externally. Right, so GenStage, why is it nice? It pushes back pressure to the boundary of the system. And it's a message contract. Everything happening here is just regular messages between processes. And GenStage is just one implementation of this contract, of those messages. So if you like the idea, but you don't like GenStage as an API, you can actually build your own abstraction that works with GenStage, because what matters is the messages that are sent behind the scenes. You as a user of GenStage, you absolutely do not have to care about this. But if you want to care, it's a possibility. And it's inspired by Akistreams, and a huge thank you to Konrad Malawski. He helped a lot answering questions, providing feedback on the design of GenStage. So, and he's from the Akka team, the Akistreams team. Yeah, so that's the overall design of GenStage, the decisions we took there. And let's just see an example to kind of solidify those ideas we have seen here. So imagine that we have 2 stages. One is a counter, is a producer. So what the counter does, it emits events starting from 0. So it's going to emit 0, 1, 2, 3, and up to infinity, right? And then you have a printer that all it does is to print those events as they come. So the counter is the producer, the printer is the consumer. We would implement the producer like this. We'd say, look, I have a module, it's a producer, I want to use GenStage. And on initialization, I'm going to say, this is a producer, and my initial state is the counter. So we can say, start counting from 0, right? We pass that as initial state. And all you have to do as a producer is to implement handle demand. And handle demand is called every every time a consumer asks you for data. So if a consumer say, hey, give me 10, handle demand is going to be called with demand equals to 10, all right? So, and then you receive your current state, which is the counter. So you're going to say, look, I'm going to generate from where I am in the counter until the counter plus demand minus 1, and I'm going to update my state. So if we're going to simulate this, to emulate this, imagine that the state starts with 0, somebody asks for 10 events, handle demand is going to return something like this. It's going to return no reply, a list from 0, 1, 2, up to 9 that gives exactly 10 elements. And it's going to say, look, my next counter now, my state is 10. So the state's 10, and then if somebody asks for 5 elements, we are going to say, look, now I'm going to return 10, 11, 12, 13, 14, and update the state as well. And then there we go, right? Just like that. So that's it. That's a very simple producer. In the consumer, it's very similar. We say, look, this is a consumer. I'm going to use GenStage. In this case, we do not use the state, so I just set the state to a random atom. The state does not matter. It could be anything. And then instead of implementing handle demand, you have to implement handle events. And what handle events does is that it receives all the events. It receives something telling us from where those events came from. And yeah, it receives the state that we don't use, and then we're going to sleep for a second. We are going to print all the events. We're going to inspect them and print them to the terminal and say, look, I don't have anything to emit because I'm a consumer, and then I return a reply. So we wrote the code. Now we can wire all them up together. So we're going to say, look, I want to start a producer with the initial counter of 0 that is going to return our counter. I want to start the consumer with the initial argument of OK, again, it does not matter, and that's going to return our printer. And then all I have to do is to subscribe the printer, which is the consumer, to the counter, the producer. And after you do this, you're going to wait a second, and then 500 events, they're going to be printed. Okay, and then you're going to wait another second, and 500 events more, they're going to be printed. And that's it. The data is flowing. Look, you didn't have to write any of the code that handles the negotiation, the back pressure. Everything's taken care for you. All you have to do is like, how do I get the data, and how I process this data? You don't have to worry about anything else. Okay, but you may be wondering, okay, that all sounds great, but why 500 events? Okay, what is happening here? So in order to answer this question, I want to very quickly talk about the subscribe options. When we called sync subscribe, there are 3 very important options that we can pass there. So one is the maximum demand, the maximum amount of events to ask. So this is like, okay, you can send me at most 1,000 events, okay? And then we have the minimum demand, which is when reached, we ask for more events. And the default is half of the maximum demand, okay? And we are going to look very closely what it means to set those values, right? And we have another option, which is the cancel option that tells how the consumer should behave if the producer shuts down. And the default is if a producer crashes, or for some reason the producer cancels the subscription, the consumer is going to crash, okay? So let's look at those, right? So what it means to set the maximum demand and the minimum demand. The easiest way to understand is to set the minimum demand to 0 and see what happens. So let's do a smaller sample size here. Let's say, look, I have a demand of 10, minimum demand of 0. So what's going to happen is that the consumer is going to subscribe to the producer and is going to say, hey, give me 10 items. The consumer is going to receive those 10 items, right? And then the consumer is going to process those 10 items. And then the consumer is going to ask for 10 more, right? This is the loop, right? I ask for 10, I receive them, I process them, and then I ask for 10 more. So what is the issue with this approach? Is that the consumer processes everything it has to, and then it asks for 10 more, and then it has to wait because you just say, hey, producer, give me 10 more, right? And then the producer is like, all right, I'm going to generate them for you. In our counter example, that's really fast. But if you're talking with SQS, it means that you have to go out, reach out to SQS, you have to parse whatever it returns to you, convert those into events and send downstream. So that's not good, right? We are just waiting. We want the computer to be efficient and be processing all the time if it can. That's why we set the minimum demand to half of the maximum demand. Because what happens in this case is this. The consumer asks for 10 items, the consumer receives 10 items, but the consumer knows that as soon as it reaches 5, it can already ask for more, right? So what it's going to do is going to say, look, I'm going to process only 5 out of 10, because I know that as soon as I reach 5, I can ask for more. So it processes only 5 out of 10, and then say, look, give me 5 more. And while the producer is producing those 5 extra, the consumer is processing the remaining 5. So ideally, assuming the producer can produce things fast enough, right? And this is evenly balanced. Everybody's working all the time, okay? So this is great. And there's one last thing I want to talk about GenStage, which is really, really important, which is the idea of GenStage dispatchers. Because all the examples we have seen so far, we still have that only straightforward pipeline. And we criticize this pipeline. That's not ideal, right? It has limitations. GenStage dispatchers is really what allows us to create a lot of interesting different topologies with GenStage. So what is a dispatcher? A dispatcher, it effectively what controls the demand and sends the data. So remember I said all this time, we don't have to worry about how we get the data, how we ask for more. We just pass some configurations and everything works. The thing that is doing most of the work behind the scenes is a dispatcher. And the dispatcher, they are per producer, and they enable concurrency by dispatching to multiple stages. So for example, the default dispatcher is the demand dispatcher. And the idea of this dispatcher is that you can have a producer with multiple consumers. So now we change the topology. It's not producer, consumer, consumer, producer, right? It's not straightforward anymore. Like it's not a single line. Now I can have a producer with multiple consumers. But now we need to choose how I'm going to choose to whom to send the data. The demand dispatcher sends it to the consumer that has the biggest demand, has the most demand available, because you assume that that's the one that's most likely to be idle soon. So imagine that we have, for consumers, we have events 1, 2, 3, 4, 5. So you can say at the beginning, everybody has the same demand. So you're going to say, I'm going to send one event to the first, another one to the second, 3 to the third, 4 to the fourth. And then imagine that in this case, the second one is the first to finish processing. Maybe it had an event that was cheaper to process. So the fifth one is going to go to the second. Okay, and that's how it's balancing the work. We also have a BroadcastDispatcher included in GenStage. You can implement your own dispatchers as well. But we have a BroadcastDispatcher as part of GenStage. And the BroadcastDispatcher just sends the events to everybody. Okay. And finally, we have a PartitionDispatcher, which allows you to control which consumer is going to process the event based on a function. So for example, if I do the reminder of the event, in this case, then 1, 5, 9 goes to the first, 2, 6, 10 goes to the second, and so on, right? So you have a function that controls this event go here, this other event goes here, and so on. And that's it. We've built this abstraction, and we in 2016 we announced it officially on the Elixir website. We announced GenStage, right? And when we announced this library, GenStage, with it we announced another library called Flow, and Flow allowed us to do the next step in that journey from eager to lazy to concurrent. With Flow, we can make our collections, right? We can process our collections concurrently by simply changing from, remember first we changed from enum to stream, now we change from stream to flow, and now we can actually process things concurrently, right? So now instead of, before we got 1, 2, 3, 1, 2, 3 with enum, and then we got 1, 1, 2, 2, 3, 3 with stream, and now with flow we get whatever, right? Because everything's being processed concurrently. One of the things that you lose when you're processing things concurrently is that you lose ordering, right? You don't know who is going to finish first. So you get things printed out of order, but we're able to achieve this concurrency step. So I'm not going to go a lot about flow. I've given other talks about it. There's a bunch of documentation how it works. But flow has a lot of powerful functionality to work with data aggregation, right? So you have map reduce, you have partitions, you can merge data, you can join data, you can configure how the demand works, you can do data windowing with triggers. You say like, look, I have this data coming all the time. I want to process those in windows in specific intervals. So it has a bunch of interesting features. You can check the repository and our documentation. But what it means for this talk, right, is that we've created GenStage, we've developed Flow, right? So we are in this journey. We started eager, lazy, concurrent, and now we are saying, look, there is the last step in this journey, right? Distributed. So it happens that writing software that is going to process data distributed is actually quite hard. So who would know, right? And so when we got into this step where we're like, okay, we believe we solved the concurrent aspect, that's the distribution, we thought, well, you know what? Let's wait, okay? Because this is a very long-term effort, and we are not even sure if this is the direction we have to go, like if it would be useful for us to build those tools, if it would be useful for the community. Because we just developed GenStage, we just developed Flow. There's a lot of potential in here, and we want to see the community using those tools first before we go ahead and say like, here's the next thing, okay? So I decided to wait. And as we waited, we could see a bunch of companies doing a lot of interesting things with GenStage and Flow. So for example, Discord, they wrote a blog post on how they could handle bursts of over 1 million messages per minute with Elixir GenStage. The Adrow folks, they wrote how they were able to save millions with Elixir and Erlang. And this is overall, they did a change of architecture. But at the end of this journey where they changed their architecture, they migrated to Flow, and they're able to, so they did a bunch of changes. Everything was already quite good. And at the end, they said, okay, let's try Flow as well. And they're able to get to double their performance when they migrated to Flow. So it's another very good article, another very good use case. And there's also, for example, the case from Forza Football, where they maximize HTTP2 performance with GenStage. I believe they were sending 1.4, 1.2 millions of messages every 10 seconds with HTTP2 and GenStage. So another nice use case. And those are just some examples. We have a bunch more examples in the community. And also working with Plataformatec, we are working with clients that are working on similar issues. And what it became clear to us is that most of the companies using GenStage and using Flow, they were using with the very specific goal of data ingestion and data processing. Okay, so what does it mean, right? So what did we see happening? So they were using GenStage because, as we saw, it gives concurrency with the dispatchers and back pressure, all right? So they were using GenStage, that's great. But they also noticed that a lot of those projects, they were re-implementing the same feature set. They were implementing rate limiting, batching, metrics, and perhaps more importantly, we noticed that all these projects, they were having the same rules, the same troubles when setting up very complex pipelines of topologies of data processing. So let's see what that means. Where is this complexity? So imagine that you've enjoyed the talk this far, and they're like, all right, I'm ready to try GenStage in our next project. And you start with this, you start simple, right? Because everything starts simple, or almost everything, but yeah. So you start, I have a supervisor, which is a 1-for-1. And then you say, I'm going to have a producer, which is going to get data from some place, and I'm going to send this to another process, which is the consumer, which is going to consume it. Very similar to our counter and printer example. So you put that under a supervision tree, because if the producer crashes, you want to restart it, and so on. All right, so this is the first step. You put it in production. It's working beautifully, and then you say, okay, I'm ready for the next step, which is, look, I'm producing this data, and I can see that consuming this data is the slow part in here. So I want to start like 4 consumers now. So I'm going to have one producer producing data, one process here that is getting data as fast as it can and send it to a bunch of other consumers, okay? So this is the first mistake, right? Why? Because the supervision strategy there is 1-for-1. What 1-for-1 means is that if one consumer crashes, the supervisor is going to restart it, right? If the producer crashes, the supervisor is going to restart it. But what you're going to see happening here is the following. If the producer crashes, because the default mechanism is that if the producer crashes, all the consumer dies, all the consumers die. If the producer crashes, what is going to happen is that all the consumers crash, and then the supervisor will be like, oh no, all my children are dying. And then it's probably going to see that, when you start a supervisor, you say, look, I can see at most like 1 failure every 5 seconds or 3 failures every 5 seconds. But in here, because you have like 5 processes here and they're all dying at the same time because the producer crashed and the producer made everything fail, the supervisor is going to go into this mode where like, okay, I got too many failures too fast, and then the supervisor is going to restart itself, bring it up in your tree. And sure, something up in your supervision tree is actually going to see that and restart that app. So it's not a big problem, right? That's how things are supposed to work. But if you want to, you may potentially see that in production. They're like, okay, I don't want that failure to cascade. So what I'm going to do is that I'm going to change the supervision strategy here from 1-for-1 to rest-for-1. And what rest-for-1 means is that if the producer crashes, everything that is after it is expected to crash as well. So when the producer crashes and all the consumers crash as well, the supervisor is cool. He's like, okay, I was already expecting that. I don't have to freak out. So, okay, so you change to rest-for-1, and then you fix that, you put in production, you're happy again, and then you're like, okay, this is working really great, but we're not maxing out the CPU yet. Okay, I have like 8 cores, you're using like 6 cores, we're about not like using everything we want. So, and then you figure out that the bottleneck, after you add some measurement somehow, you figure out that the bottleneck is actually in the producer now, right? You can actually process more data, but you're not producing fast enough. So you add another producer. So imagine that now you have like 2 producers, 4 consumers, whatever, right? So you add another producer, right? And that's the second mistake, right? Because the strategy, the rest-for-1, is no longer good for the setup anymore, right? Because if one producer dies, we are going to bring all of the consumers down, but that consumer could be consuming data from the other producer. So you don't need to bring it down anymore. So now you have to configure how you subscribe between the stages, and then you figure out, okay, so maybe I should have a supervisor for each step in my pipeline. So I have one supervisor for producers, another for consumer, and then if you want to have steps in the middle, your tree is growing bigger, right? And then you can see how the complexity is ramping up, like as you're adding stages, as you're adding steps to whatever you're processing. Right? And it's not all. We still have other issues in here, which is how are you going to handle your application shutdown? So imagine that you're processing the events in production and you have to do the deploy. So when you're doing a deploy, it means that the nodes that are currently running, eventually you have to tell them to stop. And how does the shutdown in an Elixir application, in a supervision tree works in general? Is that we stop things in the opposite order that they were started. So in here, if I have we first start the producer, right? Because we want the consumer to subscribe to the producer. So imagine that here we first started the producers and then we started the consumers, right? And then we have all these steps. If the last ones to be started, they were the consumers, it means that when we are shutting everything down, okay, the first thing that we're going to stop is the consumer, is the last step in the pipeline. And this is horrible, right? Because as soon as I stop the consumers, I can have a bunch of data in the previous steps of my pipeline that they are going to the end. And this data is never going to get to the consumer, is never going to get to the final step. Okay, so we don't want to do that. We don't want necessarily like start terminating from the end. It doesn't work well. So what we usually do is that you start like a Terminator T3000 process in here, right? That what it does is that it says it should be the last child of the supervisor at the top. And what it happens is that as soon as they look, I want to shut down my tree, the Terminator goes to supervise like, hold up, right? I know you want to shut down. Wait a second. I'm going to go to the producer and say, producer, stop getting data from the external source and flush everything you have. Let's drain this pipeline. And then the producer does that, goes back to the terminator, and then the terminator, okay, the producers are done. Let's go to the next step, flush everything, and then now let's go to the next step, and so on, so on, until you get to the consumer. You drain the whole pipeline, and then the terminator like, all right, now you can go and terminate everything, terminate the consumers all the way up to the producers, and now we don't care about the order things are terminated because we made sure that our pipeline was flushed, right? So this sounds really complex, right? Because it is, right? And we saw a bunch of teams, a bunch of companies like thinking about those challenges and solving those challenges in different ways. Okay, so what can we talk about completion stage pipelines, right? We have to ask how to structure the supervision trees correctly, how to handle graceful shutdown without data loss, how to reduce the amount of events lost during failures, right? And if by any chance you're using GenStage in production and you haven't thought about this, right, it's not the end of the world, right? The good news is that it's not the end of the world, because usually, like most well-designed data processing pipelines, you have a dead letter queue, right? So if you don't acknowledge something, you're going to retry that eventually anyway, because your data source provides that feature. Or you make these steps, and actually not or, and you usually make these steps idempotent. So if something executes more than once, right, it's not a big problem. But if you ever think about this, I want to design the best pipeline possible. If you ever think about those questions, right, you have to think about all of those things that I was talking about. And that's exactly where Broadway steps in, right? So Broadway is, as we saw, right, it's a new open source project designed at Plataformatec, and it's a new library for concurrent and multi-stage data ingestion and data processing with Elixir. That's exactly the problem we want to solve. We want to take this headache of setting up the concurrency, setting up the terminator, everything. We want to take this headache from you. You don't have to worry about it anymore, right? You just write your business logic and you get everything for free, okay? Back pressure and so on. So what can you expect from Broadway? Back pressure and concurrency, because Broadway is built on top of GenStage, okay? Automatic acknowledgements at the end of the pipeline. So usually when you're working with all those data sources, you have to say, look, I'm done with the data. Yeah, we'll take care of that for you as well. You don't have to do it. Oh, something failed. We are going to say something failed as well. You don't have to worry. Fault tolerance with minimal data loss, right? And some people, they're like, that word minimal, it's a little bit scary, right? But it's because, well, if your node goes down because there was a segmentation fault because you're doing something very weird, right? Messing up with internals that you should not of the VM or something crazy like that. Yeah, we can't protect against that, right? But all the scenarios like shutdown, errors, we have tested them out, we have designed them, and you don't have to worry. So yeah, you do get graceful shutdowns. You get batching and you get partitioning. All these out of the box. Again, all you have to do is to implement those tray functions. You don't have to do anything else. And we have recently released the version 0.2, but we are planning a bunch of other things. And we have actually, so if you go to the issues tracker, we have a bunch of issues, and we have ideas of where we want to take this, but as with everything else, we are waiting for feedback. So if you are trying Broadway out and you have feedback, or if you need a feature, come let us know, right? Because we are really looking forward to as we use feedback from our clients, we want to use feedback from the community to continue driving this to where we think it would be the ideal place, right? So we may have multiple processors. We want to have built-in metrics and statistics. This is not there yet. But it's something that is on the roadmap, and we're looking forward to have a discussion with what should be measured, so we can talk about this together. We want to have automatic backoffs in case of failures. There's a bunch of other stuff, right? So how can you help, right? So the project is, there is a warning here because the project is like really, really beta. So the first release was a little bit more, just a little bit more than a month ago. We released 0.2 like last week, or maybe it's even being released today or something like that. And then You can you can use it, you can have fun with it, so try it out, but you can also write a Broadway producer for a favorite thing. We have two producers that Plataformatec, we are maintaining for now, SQS and Broadway Rabbit MEQ. But if you have to interact with something else, you can write a producer for that. So I already saw somebody wrote a producer for Redis. We are planning to do, as part of Plataformatec efforts, a one for Kafka. Those three are the most requested by far: SQS, Rabbit MEQ, and Kafka. SQS and RabbitMQ, they are quite straightforward. I think Kafka is going to be a longer journey for us. We'll see. But the good news is, if you have a pipeline today, you have an already existing data pipeline, and you have your own GenStage producer, you can use your own producers with Broadway as well. You just have to implement something very small. And you can we have, as usual, excellent documentation, so you can check the documentation, you can check out the guides. And yeah, that's it. So very exciting work. It's really good to start on this journey, right? That started back in 2011, 2012, have some initial thoughts, and see it being developed now to Broadway and to other tools that we developed like Flow. And it's really good to be able to explore those ideas and provide another very important project. I believe is going to be very important for the community, seeing on the challenges that the community as a whole is tackling, and based on how many people raised their hands when they said they're using GenStage, right? So, yeah. And finally, I want to thank Plataformatec. We are, as you know, a software consultancy. We are the creators of Elixir, and Broadway is just one of the many open source projects that we've built and we maintain. And that's all I had for today. Thank you very much. Do we have time for questions? I'll take that as a yes. We can do is that an actual yes? Yeah, so we have microphones here at the front if you want to come closer, but people in the middle, you cannot come here to the microphone, so raise your hands and we'll figure something out. In the worst scenario, you just shout something and I will repeat the question, it's not a problem.
Hi. What if I wanted to write a producer in a different language? So if I have a legacy Rails app and I want to build consumers then in Elixir, so they would communicate over Rabbit, would that be possible, or it's a crazy idea? Or?
Yeah, that's a very good question. So for example, if the data for some reason is in another app, so because if the data is an external source, like a database, you could try connecting to that source, right? And then you talk directly to the source. But if you think about Amazon SQS, for example, it's really just an API. It's an HTTP endpoint. So if for some reason the thing that knows how to generate the data is a Rails app or anything really, as long as you write an HTTP endpoint, or if it's already there, you can connect over HTTP and that's the data over HTTP. So it's totally doable. If the data is elsewhere, you figure out a way to communicate with that place and get the data out. Thank you for the question. Yeah.
Any other questions?
Can I? I see there is some overlap between Flow and Broadway. Flow is going anywhere?
Yeah, so I was hoping somebody would ask that question, yes. So I talked about two libraries, right? Flow, which is about processing data concurrently, and Broadway, which I just talked about. And there is some overlap because they're both focusing on this idea of concurrency and how to process data as efficient as possible. And the difference is, we talk about this in the README, Flow focuses a lot on data aggregation and trying to make sense of the data as a whole, right? So for example, with Flow, if you lose, because it's about data aggregation, like the examples I usually do is like data processing, word counting, where I have to process a large corpus or a large text and get to a final answer. If I lose something, we are like, okay, it's game over. Everything goes down because the real goal is like data aggregation. And Broadway, on the other hand, is about processing each event individually. So it doesn't have like conveniences for getting to a final outcome, for example. And if something fails, you're like, oh, sure, if something fails, we are going to retry. So a bunch of the design decisions on how we structure the tree and the API we provide is really about the messages individually instead of the data as a whole. Thank you for the question. Yeah. One more. Yeah.
I have a similar question. How would you handle state in the processors?
Right. So how do you handle state in the processors? You don't. So it's as I said, it's a related question. So we've designed the processors and the batchers to not have any state in itself, which simplifies a lot in terms of how we want to react to failures. So they are stateless. You can think it's very similar to a Amazon Lambda thing where, you write the code that is going to handle that thing and that's it. Of course, you can put the state into something separate. You can put in another process, you can put in a database, but the Broadway steps, they were pretty much designed to be stateless. Another excellent question. Thank you.
Hello, thank you for your talk.
All right, thank everybody.
Here, one question more, one more question.
Oh.
I'm here.
Okay. For me, it was somebody like send everybody.
Isn't the goal of Elixir to kill all the Rabbit MQs, Kafkas, and stuff, to have only Elixir all Erlang virtual machine? Thank you.
No, it's not a goal, especially because those tools. That's an interesting question, because if we were going the distributed route where I was talking about, we would probably be very close to that. Like if you have to implement the whole distributed infrastructure, you end up implementing large parts of those libraries or those infrastructures or those tools. But our goal here is exactly to integrate with them and play well with them. So yeah, we're not looking to replace them, but actually be very good friends. Yeah.
Okay, well, thank you, Jose. Let's give him another round of applause.
Okay, so this one's for real.